As the night grows quiet and the familiar world slowly fades from attention, the mind begins to loosen its grip on ordinary ideas, allowing curiosity to drift beyond daily concerns and toward questions that rarely fit into waking life. Questions about distance and duration, about beginnings and endings, about the strange fabric that holds everything together without ever being seen. Space and time feel simple when we move through them without thinking. We walk forward, hours pass, days follow nights. Yet beneath this apparent simplicity lies something profoundly strange, something so counterintuitive that even the most basic assumptions about reality begin to dissolve the moment we look closely. Space is not empty, time is not constant, and the universe is not behaving in the way intuition suggests. Tonight, we will take our time exploring these ideas slowly and gently, without urgency and without the need to fully understand everything at once, allowing the mind to rest while curiosity remains quietly awake. Space-time is not just the background of the universe, it is the universe's structure itself. It stretches, it bends, it slows down, it connects distant events in ways that defy common sense. Light changes how time flows, gravity changes how space behaves, motion changes what now even means. These are not theories meant to overwhelm. They are discoveries that reveal how deeply unfamiliar reality becomes when we move beyond surface appearances. In this long and unhurried journey, we will explore one fact at a time, allowing each idea to settle before moving on, gently uncovering how space and time intertwine to shape everything that exists, from the smallest particles to the largest cosmic structures. There is no test at the end, nothing to memorize, nothing to solve. Only a quiet unfolding of ideas that invite the mind to relax into wonder, letting go of certainty and resting comfortably within the vastness of what we do not yet fully understand. So as you settle in, allow the pace to slow, the questions to soften, and attention to drift naturally as we begin exploring 101 mind-blowing facts about space-time, explained slowly, patiently, and without hurry. Before space became something to travel through, and before time became something to measure, both existed simply as assumptions, quiet frameworks the human mind used to make sense of motion, change, and distance, without ever questioning whether those frameworks were real or merely convenient. For most of human history, space was thought of as an empty stage, a vast container in which objects existed and moved, while time was imagined as a steady river flowing forward at the same pace everywhere, for everyone, without exception. These ideas felt obvious because they matched everyday experience. When you walk forward, space appears fixed. When hours pass, time feels uniform, yet nature does not operate according to what feels obvious. When scientists began to look closely at how light moves, how gravity behaves, and how motion changes perception, they discovered that space and time are not separate entities at all, but deeply intertwined aspects of a single structure known as space-time, a structure that does not merely host the universe, but actively shapes it. Space is not emptiness. Time is not a background clock. Space-time is a dynamic fabric, one that can stretch, bend, compress, and distort depending on energy, mass, and motion. And this realization quietly overturns centuries of intuition. In space-time, distance is not absolute. Duration is not universal. And simultaneity itself becomes uncertain. Two events that appear to happen at the same moment for one observer may not occur at the same time for another, depending entirely on how fast each observer is moving and how gravity influences their position. There is no single, universal now shared by the entire universe. This is not a philosophical idea. It is a measurable physical reality. Clocks placed on fast-moving satellites tick slightly faster than clocks on Earth. Clocks closer to massive objects run more slowly than those farther away. Time itself responds to motion and gravity. Space behaves just as strangely. Distances expand as the universe grows. Paths curve near massive objects. Straight lines are not truly straight when space-time is warped. What feels like solid, stable geometry is in fact flexible and responsive, shaped moment by moment by the contents of the universe. To understand space-time is to accept that reality is not fixed in the way intuition suggests. The universe does not provide a rigid stage on which events unfold. The stage itself participates. Space and time are not containers. They are relationships. They describe how events connect, how causes lead to effects, and how information moves through the universe at a finite speed, limited by light itself. Without light, space and time lose meaning. Without motion, duration becomes ambiguous. Without gravity, geometry becomes flat. Space-time exists not as a thing you can point to, but as a structure revealed through interaction, through how matter moves, how light travels, and how clocks behave under different conditions. This is why space-time cannot be seen directly. It can only be inferred. We observe it through bending starlight, through time dilation, through gravitational waves rippling across the cosmos, carrying information about massive events that occurred billions of years ago. Space-time remembers. It carries imprints of motion and mass, storing the history of the universe not as records, but as structure, shaping what can happen next. Nothing moves through space-time without affecting it. Nothing exists within space-time without interacting with it. Every star, every planet, every particle contributes to the geometry of reality itself, however slightly. And this means that space-time is not passive, it is active. It governs how objects move without exerting force. It guides paths without pushing. It influences outcomes without intention. Gravity in this view is not a pull, but a response. Matter tells space-time how to curve. Space-time tells matter how to move. This elegant relationship replaces the idea of invisible forces acting across empty space with a deeper, more subtle picture, one in which motion follows geometry and geometry responds to energy. Time within this structure is no longer universal. It becomes local. Each observer carries their own time, measured by the path they take through space-time. Path known as a world line, shaped by speed and gravity. Two observers may part ways and reunite, having experienced different amounts of time, not because one malfunctioned, but because space-time itself allowed their paths to diverge in duration. In this universe, aging is relative, order is flexible, causality remains intact, but intuition does not. Space-time challenges the idea that reality is the same everywhere and always. It reveals a universe where structure depends on perspective, where measurements depend on motion, and where the deepest truths are not immediately accessible to human senses. Yet despite its strangeness, space-time is remarkably consistent. Its rules apply everywhere. Its behavior is predictable. Its equations have been tested across scales ranging from atomic particles to galaxies. This consistency allows the universe to exist at all. Without space-time structure, there would be no stable orbits, no stars burning steadily for billions of years, no chemistry, no life. Space-time is not merely a scientific concept, it is the foundation of existence. And as we begin this journey through its properties, facts, and consequences, it becomes clear that understanding space-time is not about mastering equations, but about slowly releasing assumptions, allowing reality to become stranger, deeper, and more subtle than it first appears. For most of human history, it felt natural to assume that space and time had always existed, stretching infinitely into the past with no starting point, no origin, and no moment of creation, because everyday experience offers no hint that time could ever stop flowing backward, or that space could ever fail to be there. The night sky appears endless. Days follow days without interruption. Cause follows effect in a continuous chain. From this perspective, it seemed reasonable to imagine an eternal universe, one in which space provided a permanent stage and time flowed endlessly, indifferent to what happened within it. Yet when science began to examine the universe on its largest scales, this assumption quietly collapsed. The first cracks appeared when astronomers noticed something subtle but profound. Distant galaxies are not merely scattered through space, they are moving away from us, and not in random directions, but in a systematic way that reveals the expansion of space itself. This observation did not mean that galaxies were flying outward from a central point into empty surroundings. It meant something far stranger. Space itself was stretching. The farther away a galaxy is, the faster it appears to recede, not because it is moving through space at incredible speed, but because the space between galaxies is growing over time. This realization forced a radical conclusion. If space is expanding now, then in the past it must have been smaller. And if it keeps shrinking as we look further back in time, then eventually space itself must reach a state where distances go to zero. This is not merely a philosophical extrapolation. It is supported by multiple, independent lines of evidence. The cosmic microwave background, a faint glow of radiation filling the universe, reveals a time when the cosmos was hot, dense, and nearly uniform, a state that could only exist if space itself was compressed into a much smaller volume. The abundance of light elements such as hydrogen and helium matches precise predictions of nuclear processes that could only occur in an early universe that was extremely hot and dense. Together, these observations point toward a startling conclusion. Space and time as we know them did not always exist. They emerged. The beginning of space-time is often referred to as the Big Bang, but this term can be misleading because it suggests an explosion occurring at a location within space, spreading outward into emptiness. In reality, the Big Bang was not an event in space. It was an event of space. There was no outside into which the universe expanded. There was no pre-existing void waiting to be filled. Space itself came into being, along with time, energy, and the laws that govern them. To say that space-time had a beginning does not mean that something happened before it. The concept of before loses meaning when time itself has not yet emerged. Time is not a container in which events occur. It is a relationship that only exists once space-time exists. Asking what came before the beginning of time is like asking what lies north of the North Pole. The question assumes a direction that no longer applies. Near the beginning, our current understanding of physics reaches its limits. As we trace the universe backward toward its earliest moments, densities increase, temperatures rise, and space-time curvature becomes extreme, eventually reaching a point where our equations no longer produce reliable answers. This does not mean the universe stops existing, it means our descriptions stop working. At these extreme conditions, quantum effects become dominant, and gravity, which governs the shape of space-time, must be described using a theory that unites quantum mechanics with general relativity, something physics has not yet fully achieved. As a result, the true nature of the beginning remains partially hidden. Some theories suggest that space-time emerged from a quantum process, fluctuating into existence from a deeper, timeless structure. Others propose that the universe went through earlier phases, contracting and expanding, with our Big Bang representing a transition rather than an absolute origin. There are even models in which time itself behaves differently near the beginning, losing its familiar direction and becoming indistinguishable from space, making the idea of a start less sharp than everyday language suggests. What all credible theories agree on, however, is that space and time are not eternal in their current form. They are dynamic, they evolve, and they can change. This realization alters how we think about existence itself. If space-time can begin, then it is not fundamental in the deepest sense. It may be an emergent structure, arising from more basic ingredients that do not resemble space or time at all. Just as temperature emerges from the motion of particles, and pressure emerges from countless collisions, space-time may emerge from interactions at a deeper level of reality. In this view, the universe is not built within space-time. Space-time is built by the universe. The beginning of space and time marks not just the start of cosmic history, but the start of history itself. Before that point, concepts like duration, distance, and sequence have no clear meaning, and reality may be described in entirely different terms. This challenges intuition profoundly. We are accustomed to thinking of existence as something that persists through time, but if time itself has a beginning, then existence cannot be defined in the usual way. The universe does not simply exist in time. Time is one of the ways the universe exists. The beginning of space-time is therefore not a moment like any other. It is the boundary where familiar notions cease to apply. And yet, despite its mystery, this beginning left traces that we can still observe today, encoded in radiation, in cosmic structure, and in the expansion of the universe itself. The universe remembers its birth not as a story, but as geometry, temperature, and motion, written into the fabric of space-time. As we continue this journey, we will see that the beginning of space and time is not just a distant event, but something that continues to shape everything that exists now, influencing how the universe expands, how structures form, and how the future will unfold. If space and time had a beginning, then a natural and unsettling question follows, one that humanity has returned to again and again in different forms. Can space and time also come to an end, or does the universe continue indefinitely, stretching forward without limit, never truly reaching a final moment? At first, it may seem comforting to imagine that time simply goes on forever, that space continues to expand endlessly, providing an eternal backdrop for existence. After all, endings feel unnatural. They suggest closure, finality, and the loss of possibility. Yet the universe does not shape itself according to comfort. To explore whether space and time can end, we must look not at speculation, but at how the universe behaves now, because the future of space-time is written into its present structure, encoded in expansion, energy, and gravity. The universe is expanding. This much is clear. But expansion alone does not determine destiny. What matters is how that expansion changes over time. If gravity were strong enough, it could slow the expansion, stop it, and eventually reverse it, causing space to contract, galaxies to draw closer, and time to move toward a final collapse. This idea, known as the Big Crunch, imagines a universe that ends in a state similar to its beginning, where distances shrink, temperatures rise, and space-time itself becomes compressed once more. In such a scenario, time would not simply stop like a clock running out of batteries. It would approach an extreme condition where events occur closer and closer together, until the structure of space-time becomes so distorted that familiar concepts of duration and sequence lose meaning. However, observations suggest that gravity is not winning this contest. Instead of slowing down, the expansion of the universe is accelerating. Distant galaxies are not merely moving away from one another. They are doing so faster and faster over time, driven by a mysterious component known as dark energy, a form of energy that appears to be embedded in space itself. Dark energy behaves very differently from matter. While matter clumps and pulls inward through gravity, dark energy seems to push space apart, causing expansion to accelerate as space grows larger. If dark energy remains constant or grows stronger, the universe may continue expanding forever, leading to a future where galaxies drift beyond each other's horizons, stars burn out, and space becomes increasingly cold and empty. In this scenario, known as the Big Freeze or heat death, time does not end abruptly. It stretches on, but with fewer events, less structure, and diminishing complexity. Stars exhaust their fuel, black holes slowly evaporate, matter becomes sparse. Time continues, but nothing significant happens. This raises an important distinction. The end of space-time does not necessarily mean the end of time itself. It can also mean the end of meaningful change. A universe can persist while becoming effectively timeless, not because time has stopped, but because there is nothing left to mark its passage. Yet other possibilities exist. Some theories propose that dark energy may not be constant, but dynamic, capable of increasing in strength over time. If this is the case, the expansion of space could accelerate so violently that it eventually overcomes all other forces, tearing apart galaxies, stars, planets, and even atoms themselves. This hypothetical future is known as the Big Rip. In a Big Rip scenario, space-time does not fade quietly, it fractures. Distances grow so rapidly that the structure of matter cannot hold together, and even the concept of a stable object ceases to apply. Time still exists, but it becomes fragmented, dominated by extreme expansion that prevents continuity. In the final moments, if such moments can even be defined, space-time itself may be pulled apart, leaving no framework within which events can occur. Here, the end of space-time is not a boundary, but a breakdown. There are also more subtle possibilities. Some models suggest that space-time could transition into a different phase, much like water freezing into ice or boiling into vapor. In such a transition, the familiar dimensions of space and time might reorganize, giving rise to a new structure with different properties. From within our current universe, this would appear as an ending. From a deeper perspective, it might be a transformation. In these models, space-time does not vanish. It changes form. There are even ideas in which time does not end but loses its direction. The arrow of time, defined by increasing entropy, could fade if the universe reaches a state of maximum disorder, where no meaningful distinction exists between past and future. In such a universe, time still exists mathematically, but psychologically and physically it becomes irrelevant. No processes occur that distinguish one moment from the next. The universe becomes static in every meaningful sense. Whether space and time can truly end depends on what we mean by end. Does it mean a final moment, beyond which nothing exists? Or does it mean a loss of structure, motion, and change? From a physical standpoint, an absolute end of time is difficult to define because time is not an object that can simply stop. It is a relationship between events. As long as events occur, time exists. When events cease, time loses its role. This suggests that the fate of space-time is not a single outcome, but a spectrum of possibilities, each defined by how the universe's contents evolve and how the geometry of space responds. What is certain is that space-time is not immutable. It can begin, it can change, and under the right conditions it can become unrecognizable. Whether this transformation lies in a distant future or in a form we cannot yet imagine remains an open question. The universe has surprised us before. What once seemed eternal has proven temporary. What once seemed fixed has revealed flexibility. Space and time, which feel so fundamental to existence, may themselves be phases in a larger, deeper reality, one in which beginnings and endings are not absolute, but transitions between forms we are only beginning to understand. And as we move forward in this exploration, we will see that the possible end of space-time is not merely a question about the distant future, but a window into what space and time truly are, and how fragile, dynamic, and remarkable the structure of reality really is. In everyday life, motion feels simple and intuitive. You walk across a room, drive along a road, or watch clouds move slowly across the sky, and time seems unaffected by any of it, continuing to flow at the same steady pace regardless of how fast or slow things appear to move. For centuries, this experience shaped the belief that time is absolute, the same everywhere, for everyone, independent of motion. Yet the universe does not agree with this intuition. When scientists began to measure the behavior of light with extreme precision, they encountered a result that quietly overturned this comfortable picture. The speed of light is the same for all observers, no matter how fast they are moving. This single fact, simple to state and difficult to accept, forced a complete rethinking of space and time. If the speed of light is fixed, then something else must change to accommodate motion, and what changes is time itself. To understand this, imagine two observers. One is standing still, while the other moves past at an enormous speed, close to the speed of light. Each carries a clock. From their own perspective, both clocks appear to tick normally. Nothing feels different. Nothing feels slow. But when each observer looks at the other, they see something extraordinary. the moving clock ticks more slowly. This effect, known as time dilation, is not an illusion or a trick of perception. It is a real, measurable difference in how time passes for objects in motion relative to one another. The faster an object moves through space, the more slowly it moves through time. This idea feels paradoxical only because human experience is limited to speeds far below the speed of light, where time dilation is too small to notice. But in the universe at large, where particles routinely travel near light speed, time dilation is a fundamental feature of reality. Subatomic particles created high in Earth's atmosphere provide a striking example. These particles should decay almost instantly, yet many survive long enough to reach the ground, not because they have changed, but because from our perspective, their internal clocks are running more slowly due to their immense speed. From the particle's own perspective, nothing unusual happens. Its lifetime feels normal. It is the relationship between observers that changes. This reveals a crucial truth. There is no single, universal time shared by all observers. Each object carries its own time, shaped by how it moves through space. Motion does not merely occur in time, it reshapes time. As speed increases, the effects become more dramatic. At speeds approaching that of light, time dilation grows without limit. In principle, an object moving at exactly the speed of light would experience no passage of time at all. This does not mean light is frozen. It means that time, as measured along light's path, collapses to zero. Light does not age. It does not experience duration. For a photon travelling across the universe, the moment of its emission and the moment of its absorption are separated by no time at all, even though billions of years may pass for the rest of the universe. This challenges the very idea of simultaneity. Events that appear to occur at the same time for one observer may not occur at the same time for another observer moving at a different speed. There is no global present moment that everyone agrees on. The universe does not possess a single now. Instead, each observer defines their own slice of time through space-time, shaped by motion and perspective. These slices overlap, but they are not identical. This means that past, present, and future are not absolute categories. They depend on how an observer moves through the universe. Motion, therefore, does not merely change how fast time flows, it changes how time is ordered. Events that one observer considers simultaneous may be ordered differently by another. Causality remains intact. Causes still precede effects, but the structure of time becomes flexible rather than rigid. This flexibility is not optional. It is built into the geometry of space-time itself. Every object follows a path through space-time called a world line, and the amount of time that object experiences depends on the shape of that path. Different paths through the same region of space-time can have different lengths in time, even if they begin and end at the same events. This leads to outcomes that feel deeply counterintuitive. Two clocks can start together, separate and reunite, showing different times, not because one malfunctioned, but because each followed a different path through space-time. Time becomes personal. Yet this does not mean reality is subjective or chaotic. The rules governing time dilation are precise, consistent and universal. They apply equally to all observers, regardless of perspective. What changes is not the laws of physics, but the relationship between measurements. Motion reveals that time is not a background river flowing independently of the universe. It is part of the structure of reality itself, intertwined with space, responsive to speed, and shaped by geometry. Once this is understood, it becomes impossible to return to the old idea of a single universal time. The universe does not run on one clock. It runs on countless clocks, each ticking according to the path taken through space-time. And as we continue, we will see that motion is only one way time can be altered. Gravity too reshapes time in profound and unexpected ways, bending duration itself in response to mass and energy. If motion reveals that time can stretch and slow, gravity reveals something even more unsettling. Time does not flow at the same rate everywhere, even when nothing is moving, because the presence of mass and energy reshapes space-time itself, altering how duration is experienced from one location to another. In everyday life, gravity feels simple. Objects fall, planets orbit, weight presses downward. It feels like a force acting within space. But at a deeper level, gravity is not a pull at all. Gravity is the curvature of space-time. Mass and energy bend the fabric of space-time, and this bending affects not only how objects move through space, but also how time itself passes. The stronger the gravitational field, the more time slows. This means that a clock placed closer to a massive object will tick more slowly than a clock farther away, even if both clocks are perfectly still relative to each other. This effect, known as gravitational time dilation, is subtle on Earth, but profound near extreme objects like neutron stars and black holes. On the surface of our planet, time flows slightly more slowly than it does for satellites orbiting high above. The difference is tiny, measured in billionths of a second, but it is real, measurable, and essential to modern technology. Global positioning system satellites must correct for gravitational time dilation. Without these corrections, GPS errors would accumulate rapidly, making precise navigation impossible. This is not theory, it is daily engineering. Gravity slows time because mass alters the geometry of space-time. Near a massive object, space-time curves more strongly, and the path through time becomes shorter per unit of distance travelled. To visualize this, imagine space-time as a stretched fabric. A heavy object creates a deep depression. Paths near that depression are distorted. An object at rest near a massive body is still moving through space-time, but its trajectory is shaped by the curvature created by gravity, causing less time to elapse compared to a similar object farther away. From the perspective of an observer far from the gravitational source, processes near the massive object appear slowed. Clocks tick more slowly. Biological processes unfold more gradually. Even radioactive decay takes longer. From the perspective of the object itself, nothing feels different. Its local time feels normal. This reveals a profound truth. There is no single, universal flow of time. Time is local. Each region of space-time has its own rate of time flow, determined by the distribution of mass and energy. As gravity increases, time slows more dramatically. Near a neutron star, where matter is compressed to densities far beyond anything on Earth, time dilation becomes significant. A clock near the surface of such a star would run noticeably slower than one far away. Near a black hole, this effect becomes extreme. As an object approaches the event horizon of a black hole, time dilation relative to distant observers increases without bound. From the outside, it appears that the object's clock slows to a near halt, never quite reaching the horizon within finite time. To the falling object, however, time continues normally. It crosses the horizon without noticing anything unusual at that moment. This dual perspective highlights the relational nature of time. Time does not belong to space-time as a whole. It belongs to paths through space-time. Gravity shapes those paths. The deeper the gravitational well, the steeper the curvature of time, and the more dramatically duration stretches between observers at different positions. This has startling implications. It means that time passes differently at different heights above Earth's surface. Your head ages slightly faster than your feet. The difference is incredibly small, but it exists. It means that civilizations living near massive objects would experience time differently from those far away. Their histories would unfold at different rates. It means that in a universe with varied gravitational landscapes, there is no single cosmic time shared by all beings everywhere. Gravity does not merely govern motion, it governs duration. This understanding replaces the old idea of gravity as a force acting through space with a deeper, more elegant picture. Gravity is geometry, and time is part of that geometry. Mass tells space-time how to curve. That curvature tells time how to flow. This also explains why gravity cannot be shielded or turned off. It is not something applied to objects. It is the structure within which objects exist. Even empty space possesses gravitational properties if energy is present, because energy itself contributes to space-time curvature. Time slowing in gravitational fields is not a side effect. It is a direct consequence of how reality is organized. Once this is understood, gravity becomes less mysterious and more profound. It is no longer an invisible hand pulling objects together. It is the shape of reality guiding motion and duration simultaneously. As we continue, we will see that when motion and gravity act together, time becomes even more flexible, leading to effects that reshape our understanding of aging, simultaneity, and the limits of experience itself. When motion and gravity are considered separately, each already challenges intuition by revealing that time can slow, stretch, and differ from one observer to another. But when motion and gravity act together, their combined influence reshapes reality even more deeply, revealing that space and time are not merely flexible, but inseparable aspects of a single dynamic structure. In the universe, motion rarely occurs without gravity, and gravity rarely acts on objects that are not moving. Planets orbit stars. Stars orbit galactic centers. Galaxies drift through expanding space. Every object follows a path through space-time that is shaped simultaneously by its speed and by the curvature created by mass and energy around it. This path determines how much time the object experiences. An object in motion through space-time divides its movement between space and time. The faster it moves through space, the less it moves through time. At the same time, if it is deep within a gravitational field, the curvature of space-time further reduces the rate at which time passes along its path. These two effects do not compete, they combine. This means that time dilation due to motion and time dilation due to gravity stack together, producing outcomes that can be precisely calculated and experimentally verified. A satellite orbiting Earth is a perfect example. It moves at high speed relative to the surface, which causes its onboard clocks to run more slowly due to motion-based time dilation. At the same time, it resides higher in Earth's gravitational field, where gravity is weaker, causing its clocks to run faster due to gravitational time dilation. The net effect is a balance between these two influences. Without correcting for both, satellite-based systems would quickly drift out of sync with clocks on the ground. This is not an abstract idea. It is an everyday application of space-time physics. The universe constantly balances motion and gravity to determine how time flows along every possible path. This balance becomes especially dramatic near massive compact objects. Near a black hole, gravity slows time enormously, if an object is also moving at relativistic speeds. The combined effect can cause time to pass extraordinarily slowly relative to distant observers. Yet from the object's own perspective, its internal processes continue normally. This duality highlights one of the deepest truths of space-time. There is no preferred reference frame. No observer's time is more real than another's. Each is valid within its own path through space-time. Reality is not built around a single perspective. Instead, reality is built from relationships between perspectives, connected by the geometry of space-time and constrained by the speed of light. Motion and gravity together determine not only how fast time passes, but also how events are ordered. In regions where space-time is strongly curved, such as near black holes or in the early universe, the distinction between past, present, and future can blur in unexpected ways. Paths through space-time can tilt so dramatically that what one observer considers a future event may lie in the past of another observer's reference frame, as long as causality is preserved. This does not allow time travel in the ordinary sense, but it reveals that time structure is far more complex than a simple, forward-flowing line. Space-time can be warped to such an extent that different observers carve it into slices of now that intersect differently, yet remain consistent with the laws of physics. This is why simultaneity is not absolute. Motion and gravity together define which events can influence which others, shaping light cones that determine the possible flow of information and causation. Every event exists within a cone of influence defined by the speed of light and the curvature of space-time. Outside this cone, events cannot affect one another, regardless of how time is defined. This structure preserves causality even as time becomes flexible. The universe allows time to stretch, slow, and vary, but it does not allow cause and effect to reverse. Motion and gravity also shape the large-scale evolution of the universe. The expansion of space itself is a motion, one driven by the distribution of matter, radiation, and dark energy, and governed by the geometry of space-time. As galaxies move apart, their relative motion causes time dilation between distant regions, while the gravitational influence of matter slows time in dense structures like galaxy clusters. On cosmic scales, time does not flow uniformly. Different regions of the universe experience cosmic history at slightly different rates, depending on their motion and gravitational environment. This means that the universe does not evolve in perfect synchrony everywhere. There is no universal cosmic clock ticking in the background. Instead, there is a web of local times, each shaped by motion and gravity, all interconnected through space-time's geometry. Even the early universe reflects this interplay. In the moments after the Big Bang, space-time curvature was extreme, densities were enormous, and motion was ubiquitous. time flowed very differently than it does now. As the universe expanded and cooled, space-time flattened, gravitational influences spread out, and time gradually settled into the more familiar behavior we experience today. The flow of time we experience is not fundamental. It is emergent. It arises from the current state of space-time, shaped by the distribution of energy and motion in the universe. If the universe were to evolve into a very different configuration, time would behave differently as well. Motion and gravity together define the rhythm of reality. They determine how long processes take, how structures form, and how information flows. They shape aging, causality, and the very notion of sequence. Without motion, time would lose meaning. Without gravity, space would lack structure. Without space-time geometry, there would be no universe as we know it. Understanding how motion and gravity combine is not just about understanding clocks or orbits. It is about understanding why reality has order at all. Space-time provides a framework in which change can occur without chaos, allowing the universe to evolve while preserving consistency. This delicate balance is not accidental. It is the result of deep principles encoded into the structure of space-time itself, principles that continue to govern everything from the smallest particle interactions to the fate of the cosmos. As we move forward into the next major part, we will begin exploring how space-time behaves on the largest possible scales, revealing facts that challenge not only intuition, but the limits of imagination itself. For most of human history, space was imagined as emptiness, a vast nothingness separating objects from one another, an invisible void through which planets move and stars shine, but which itself does nothing, contains nothing, and influences nothing. This idea feels natural because our senses give us no reason to think otherwise. We cannot touch space, we cannot see it directly. It appears silent, passive, and inert. Yet this picture is deeply misleading. Space is not empty, it is active. Even when all matter is removed, even when no particles, atoms, or radiation remain, space itself continues to possess structure, energy, and physical properties that influence how the universe behaves. This realization emerged gradually as physics pushed beyond everyday experience and began probing the deepest foundations of reality. One of the first clues came from the behavior of light. Light does not travel arbitrarily fast. It travels at a precise universal speed that depends on the properties of space itself. If space were truly nothing, there would be no reason for light to have a fixed speed. Yet it does. This suggests that space has characteristics that govern how information moves through it, much like a medium governs the propagation of waves, even though space is not a substance in the classical sense. As physics advanced, this insight deepened. Quantum theory revealed that what we call empty space is never truly empty. At the smallest scales, space is filled with activity, a restless background of quantum fluctuations in which energy briefly appears and disappears. Particles flicker into and out of existence, and fields remain active even in their lowest possible energy state. This is known as the quantum vacuum, and it is anything but nothing. Virtual particles constantly form and annihilate within it. Fields vibrate subtly, even when no particles are present. Energy persists as a baseline, unavoidable feature of space itself. This means that emptiness has energy, and energy, according to general relativity, affects space-time curvature. So even a perfectly empty region of space still contributes to the structure of the universe. This has real, measurable consequences. One striking example is the Casimir effect, in which two uncharged metal plates placed extremely close together experience a force that cannot be explained by classical physics alone. The force arises because the quantum vacuum behaves differently between the plates than outside them, creating a measurable pressure. Empty space pushes. Another consequence appears on cosmic scales. The expansion of the universe is driven not only by matter and radiation, but by energy inherent to space itself, what we observe as dark energy. Dark energy does not dilute as space expands. It remains constant per unit volume of space. This means that as the universe grows larger, the total amount of dark energy increases, not because energy is being created from nothing, but because space itself carries energy as a fundamental property. In this sense, space is not a backdrop for the universe, it is one of its contents. Space participates in cosmic evolution. It stretches, it stores energy, it responds to matter. When galaxies move apart, they are not travelling through empty nothingness. They are carried by the expansion of space itself, a process governed by the properties of space-time rather than by motion through a void. This expansion does not require space to expand into anything. There is no outside. Space expands by changing its own internal geometry. This makes it clear that space is not a container. It is a dynamic entity. Even its geometry is not fixed. Space can be flat, positively curved, or negatively curved depending on the total energy and matter content of the universe. This curvature determines whether parallel lines remain parallel, whether triangles add up to 180 degrees, and how light travels across cosmic distances. These are not abstract mathematical curiosities. They affect how we see the universe. Light from distant galaxies bends as it passes through regions of curved space-time, producing gravitational lensing that allows us to map invisible matter and probe the structure of space itself. Space bends light. This bending does not require a force acting on light. Light simply follows the geometry of space-time. If space were nothing, there would be nothing to bend. The fact that it bends reveals its physical reality. Space also has a temperature. The universe is filled with the cosmic microwave background, a faint radiation field that gives space a temperature just a few degrees above absolute zero. Even in the emptiest regions between galaxies, this background persists, bathing space in residual energy from the early universe. Space remembers its past. It carries imprints of conditions that existed billions of years ago, preserved not as objects but as fields, radiation, and geometry. This memory shapes what can happen next. Structure formation, galaxy evolution, and the growth of cosmic webs all depend on how space responds to energy and matter over time. Space is not merely affected by the universe, it is part of the universe. This challenges the intuition that objects exist in space like fish in water. A better analogy is that objects in space coexist as parts of a single system, each influencing the other. Matter shapes space. Space shapes matter. Without space's structure, particles would not have stable paths. Without space's energy, cosmic expansion would behave differently. Without space's geometry, time itself would lose coherence. Space is not a passive stage. It is an active participant. This realization forces a profound shift in how we think about reality. We do not live in a universe where things exist in space. We live in a universe where things exist with space. Space is not emptiness between objects. It is a fundamental component of existence, rich with structure, energy, and influence, quietly shaping every motion, every interaction, and every moment of time. And as we move forward, we will see that space is not only active but also limited, curved, and deeply connected to time in ways that continue to challenge even the most advanced theories of physics. When people imagine the universe, they often picture something vast but ultimately bounded, a gigantic sphere or container with an edge, beyond which lies either nothing or some mysterious unknown. This image feels natural because the human mind evolved to understand spaces with boundaries, rooms with walls, landscapes with horizons, and oceans with shores. Yet space does not behave like any of these familiar environments. One of the most profound discoveries of modern cosmology is that space may have a shape without having an edge, meaning the universe can be finite without being bounded, a concept that challenges intuition but follows directly from the geometry of space-time. To understand this, it helps to separate two ideas that are often confused: size and shape. Size tells us how much space there is. Shape tells us how that space is arranged. A surface can be finite yet unbounded. The surface of a sphere is a simple example. If you travel on the surface of a sphere, you can keep going indefinitely without ever encountering an edge. Yet the total area of the surface is finite. The surface curves back on itself. In higher dimensions, space itself can behave in an analogous way. If the universe has positive curvature, it may be finite but unbounded, meaning there is a limited amount of space, but no edge where space suddenly stops. In such a universe, travelling far enough in one direction could eventually bring you back to your starting point, not because space loops like a circle in ordinary dimensions, but because its geometry closes in on itself in higher dimensions. This is difficult to visualize because our intuition is built in 3 dimensions, but the mathematics is precise and well defined. Alternatively, the universe may be flat or negatively curved, in which case space could be infinite, extending endlessly in all directions without repeating. Observations suggest that on large scales the universe is very close to flat, but this does not conclusively rule out slight curvature, especially on scales larger than we can observe. The observable universe is limited by the speed of light and the age of the cosmos. We can only see as far as light has had time to reach us since the beginning of space-time. Beyond this horizon, space may continue, structured in ways we cannot yet measure. This means that even if the universe is infinite, we only ever have access to a finite portion of it. The limits we perceive are not limits of space itself, but limits of observation. This distinction is crucial. The universe may not have an edge, but our knowledge of it does. Space may extend far beyond what we can see, carrying structures, galaxies, and perhaps regions very different from our own. Or it may curve back on itself, forming a closed geometry that is finite yet endless. Both possibilities are consistent with current evidence. What determines the shape of space is its total energy content, including matter, radiation, and dark energy. These components influence curvature, expansion, and geometry through the equations of general relativity. A universe dominated by matter tends toward positive curvature, A universe dominated by dark energy tends toward flat or negatively curved geometry. The balance between these components determines not only the universe's shape, but also its long-term fate. The shape of space affects how structures form. In a positively curved universe, large-scale structure evolves differently than in a flat or negatively curved one. Light travels along different paths. Parallel lines may converge or diverge. These effects influence how we measure distances and infer the universe's history. This is why cosmologists study subtle patterns in the cosmic microwave background. Tiny temperature variations across the sky encode information about the universe's geometry, revealing how space has expanded and curved since the earliest moments of cosmic history. By measuring these patterns, scientists can infer whether space is flat, closed, or open. So far, the evidence suggests remarkable flatness. But this flatness may be a result of early cosmic inflation, a rapid expansion that smoothed out curvature, making space appear nearly flat, even if its global shape is more complex. Inflation itself hints that space may be far larger than the observable universe, possibly infinite, with regions far beyond our horizon that we will never see. In such a scenario, the universe is not just vast, it is effectively unbounded in practice. This raises deep philosophical questions. If space is infinite, then every possible configuration of matter may occur somewhere, repeated endlessly across cosmic distances. If space is finite but unbounded, then the universe is self-contained, complete in itself, with no exterior. In either case, there is no edge in the usual sense. There is no place where space stops and something else begins. The idea of an edge of space is a remnant of everyday intuition, not a feature of physical reality. Space does not end. It either continues or curves. The shape of the universe is therefore not a matter of speculation, but a measurable physical property, one that determines how space behaves on the largest scales and how time unfolds within it. As we move forward, we will see that space's shape is not static. It evolves. Expansion changes distances. Energy changes curvature. Time changes geometry. Space is not frozen in form. And in the next part, we will explore how space stretches, expands, and carries galaxies along with it, revealing one of the most counterintuitive facts of all, that objects can move apart faster than light without violating the laws of physics. At first glance, the idea that space can expand faster than the speed of light sounds like a direct violation of one of the most famous rules in physics, the principle that nothing can travel faster than light. This rule feels absolute, almost sacred, because it lies at the heart of modern physics and has been confirmed by countless experiments. And yet, on the larger scales of the universe, space itself does exactly that. Galaxies can move away from one another faster than light, not occasionally, not hypothetically, but continuously. And this does not break any physical law. To understand why, we must let go of a deeply ingrained assumption that motion through space and the expansion of space are the same thing. They are not. The speed limit imposed by the speed of light applies to objects moving through space, not to the expansion of space itself. This distinction is subtle but fundamental. When an object moves through space, it carries information, energy, and causality along its path. If it were to move faster than light, it could violate causality, allowing effects to precede causes, breaking the logical structure of the universe. But when space itself expands, no object is locally outrunning light. Instead, the distance between objects increases because the geometry of space changes. Imagine two galaxies sitting still relative to their local space. They are not firing rockets. They are not moving through space. Yet over time, the space between them stretches, increasing their separation. From each galaxy's local perspective, nothing unusual is happening. Physics behaves normally. Light still travels at the same speed. Clocks tick normally. But from a global perspective, the distance between them grows, and if that distance grows fast enough, their separation can increase at an effective rate greater than the speed of light. This does not mean one galaxy is sending signals faster than light to the other. In fact, once galaxies are separated by enough expanding space, light emitted by one may never reach the other at all. This leads to the concept of the cosmic horizon. There are regions of the universe so distant that the expansion of space between us and them is so rapid that light from those regions can never reach us, no matter how long we wait. These regions are not beyond space. They are within space, but carried away by its expansion. This does not violate relativity because relativity is a local theory. It governs what happens in small regions of space-time, where space can be approximated as flat and expansion is negligible. On these local scales, nothing outruns light. On cosmic scales, however, space-time itself evolves, and distances are not fixed. This distinction allows the universe to expand faster than light without breaking the rules that govern motion and causality. The expansion of space is described by a quantity known as the Hubble parameter, which tells us how fast space is expanding per unit distance. The farther away a galaxy is, the more space lies between it and us, and the faster that space expands. This means that at sufficiently large distances, the expansion rate multiplied by distance exceeds the speed of light. There is nothing special about this distance. It is not a barrier or boundary. It simply marks where expansion dominates over light's ability to bridge the gap. In the early universe, this effect was even more extreme. During a brief period known as cosmic inflation, space expanded at an enormous rate, causing regions that were once extremely close to be driven far apart in a tiny fraction of a second. During inflation, distances grew far faster than light could travel, smoothing out irregularities and explaining why the universe appears so uniform on large scales today. Again, no object moved through space faster than light. Space itself expanded. This distinction resolves what might otherwise seem like a contradiction. The speed of light is a limit on how fast information can travel within space-time. It is not a limit on how fast space-time itself can change. Space-time is not an object inside the universe. It is the structure of the universe. Its evolution is governed by different rules. This also explains why distant galaxies appear to be receding from us in all directions. We are not at the center of expansion. Every observer sees the same pattern. From any galaxy, all sufficiently distant galaxies appear to move away because space expands uniformly everywhere. There is no center. There is no edge. Expansion happens everywhere at once. As space expands, it stretches the wavelengths of light traveling through it, causing distant galaxies to appear redshifted. This redshift is not due to motion through space like the Doppler effect in sound. It is due to the stretching of space itself. Light loses energy as space expands, not because it slows down, but because the geometry it travels through changes. This further reinforces the idea that space is active, dynamic, and influential, not a passive background. The fact that space can expand faster than light has profound implications for the universe's future. As expansion accelerates, more regions will cross beyond our cosmic horizon, becoming permanently unreachable. The observable universe will shrink in a relative sense, not because space is collapsing, but because expansion isolates regions from one another. Yet locally, nothing dramatic happens. Stars continue to orbit galaxies, atoms remain bound, light continues to move at the same speed. The expansion of space operates primarily on the larger scales, leaving smaller structures intact. This layered behavior reveals the elegance of space-time. Different rules dominate at different scales, yet they remain consistent with one another. The universe allows space to expand faster than light without allowing information to do the same, preserving causality while permitting vast cosmic evolution. This is one of the most counterintuitive truths about reality. The universe is not constrained by human intuition. It is constrained by deeper principles that only reveal themselves when we step back and look at the largest possible picture. Space can stretch faster than light. Time can flow at different rates, and yet the laws of physics remain intact. What seems impossible at first becomes inevitable once the true nature of space-time is understood. And as we continue into the next major part, we will see that these strange behaviors are not rare exceptions, but everyday features of the universe at its deepest level, quietly shaping reality far beyond the reach of ordinary experience. For as long as humans have been aware of change, time has felt like the most reliable feature of existence, a steady and universal flow moving forward at the same pace for everyone, everywhere, regardless of place, motion, or circumstance. We wake, the sun rises, hours pass, night returns. This regularity creates the powerful illusion that time itself is absolute, an invisible river carrying the universe forward in perfect synchrony. Yet this intuition, though deeply ingrained, is fundamentally wrong. Time is not a universal flow. It does not tick at the same rate everywhere, and it does not define a single shared present for the entire universe. Time is local. Each observer carries their own time, shaped by motion, gravity, and the path they take through space-time, and there is no higher cosmic clock against which all others can be compared. This idea is unsettling because it undermines the notion of a single now, a universal moment that exists simultaneously everywhere. In everyday life, we assume that when something happens now, it happens now for the entire universe. But physics reveals that this assumption has no physical meaning. Two events that are simultaneous for one observer may not be simultaneous for another observer moving at a different speed or existing in a different gravitational field. There is no contradiction here. Both perspectives are equally valid. This phenomenon arises because time is woven together with space into a four-dimensional structure, and different observers slice that structure in different ways, depending on their motion and position. Imagine space-time as a vast landscape. Each observer moves through it along a path. What one observer labels as present is simply a cross-section of that landscape chosen by their motion. Another observer, moving differently, cuts the landscape along a different angle, producing a different set of events they consider simultaneous. There is no preferred slicing. The universe does not privilege one observer's present over another's. This means that the past, present and future are not absolute divisions built into reality. They are relational. What is in the future for one observer may already lie in the past for another, as long as no causal connection is violated. Causality remains intact. Effects do not precede causes. But the ordering of events outside causal influence is flexible. This leads to a picture of the universe often described as a block universe, where all events, past, present, and future, exist within the structure of space-time, and the flow of time is not a property of the universe itself, but of how conscious beings experience their path through it. In this view, time does not pass in an objective sense. Instead, consciousness moves along a world line, experiencing events sequentially. The universe simply is. This doesn't mean that change is an illusion, or that the future is predetermined in a simplistic way. It means that change is a feature of relationships between events, not a global ticking clock. The laws of physics describe the universe as a network of events connected by space-time geometry, not as a sequence unfolding frame by frame. This realization forces a deep shift in how we think about existence. If there is no universal present, then the idea that the entire universe shares a single moment becomes meaningless. There is no cosmic now sweeping across the stars. Instead, there are countless local nows, each defined by an observer's state of motion and gravitational environment. This does not affect everyday life, because at human speeds and gravitational conditions, differences are extremely small. Our clocks stay in sync well enough for practical purposes, but on cosmic scales and at extreme speeds or gravitational fields, these differences become undeniable, time fragments. This fragmentation is not a breakdown of reality, it is a revelation of its structure. Time was never a single universal flow. It only appeared that way because our experience is limited to a narrow range of conditions. When physics expands that range, time reveals its true nature. Time becomes something closer to a dimension than a process, a coordinate rather than a current. Yet even as time loses its universality, it retains order. Events are still connected. Causes still precede effects. The universe remains coherent. What disappears is the comforting idea that everyone shares the same temporal perspective. Instead, reality offers something richer and more subtle. A universe where time adapts to context, where duration and simultaneity depend on motion and gravity, and where no single viewpoint holds absolute authority. Understanding this does not make time meaningless. It makes it relational. Time is not something the universe experiences. It is something that arises from how parts of the universe relate to one another. And as we continue, we will see that this relational nature of time leads to even deeper consequences, including the possibility that time itself may not be fundamental but emergent, arising from deeper structures that do not resemble time at all. Even after learning that time is not universal, that it flows at different rates and depends on motion and gravity, there remains one aspect of time that feels stubbornly absolute: its direction. Time seems to move forward, memories point backward, causes come before effects, eggs break, but never unbreak. This one-way character of time is known as the arrow of time, and unlike time dilation or relativity, it is something we experience directly, constantly, and without exception. Yet here is the paradox. At the deepest level known to physics, the fundamental laws that govern particles, fields, and forces do not care about direction. They work almost perfectly the same whether time runs forward or backward. If you were to record the motion of particles colliding, atoms vibrating, or planets orbiting, and then play that recording in reverse, the underlying equations would still make sense. Nothing in those equations says which direction is the correct one. So where does the arrow of time come from? Why does the universe clearly distinguish between past and future, when its basic rules do not? The answer lies not in time itself, but in entropy. Entropy is a measure of disorder, or more precisely a measure of how many microscopic arrangements correspond to a macroscopic state. Systems naturally evolve from states of lower entropy to states of higher entropy, not because they are pushed to do so, but because there are vastly more disordered states than ordered ones. A neatly stacked deck of cards represents a very special low entropy arrangement. A shuffled deck represents one of countless high entropy arrangements. Left alone, systems move toward what is statistically most likely. This statistical tendency defines the arrow of time. When entropy increases, time points forward. When entropy decreases, time would appear to run backward. In our universe, entropy has been increasing since the beginning. The early universe was extraordinarily smooth, uniform and ordered, a state of remarkably low entropy given its energy content. As the universe expanded, gravity allowed matter to clump, stars to form, and structure to emerge, all while overall entropy continued to rise. This initial low entropy condition is the ultimate source of time's direction. It is not that time itself forces entropy to increase. It is that the universe started in a state where entropy could increase. Every process we associate with time's arrow traces back to this fact. We remember the past because memory formation increases entropy. We cannot remember the future because doing so would require entropy to decrease. Heat flows from hot to cold because that direction increases entropy. The reverse would be extraordinarily unlikely, though not forbidden by the laws of physics. Life itself depends on this imbalance, feeding on energy gradients that exist only because entropy is increasing overall. Without the arrow of time, there would be no aging, no learning, no causation as we understand it. Yet the arrow of time is not embedded in the fabric of space-time in the same way as motion or gravity. It is emergent. It arises from boundary conditions, from how the universe began, not from how its laws operate moment to moment. This means that time's direction is not absolute, in the same way its flow is not universal. In principle, if a region of the universe existed where entropy decreased, the arrow of time there would point in the opposite direction. Such regions are not known to exist, but the laws of physics do not strictly forbid them. This raises a deeply unsettling possibility. The arrow of time is not a fundamental feature of reality. It is a consequence. It depends on the state of the universe. If the universe had begun in a high entropy state, time would not have had a clear direction at all. The past and future would blur, and meaningful processes would not exist. The fact that time has a direction is therefore a reflection of the universe's initial conditions, not an inherent necessity. This also means that the arrow of time could change. In a far future universe approaching maximum entropy, where no significant energy gradients remain, the arrow of time may lose its meaning. Events would still occur in a technical sense,
but nothing would distinguish one moment from another. Time would exist mathematically, but not experientially. There would be no clocks worth reading, no processes that mark change. The arrow would fade. Understanding the arrow of time forces us to confront the idea that what feels most fundamental about time may actually be fragile, contingent, and temporary. Time points forward not because it must, but because the universe allows it to. And this realization opens the door to even deeper questions. If the arrow of time is emergent, could time itself be emergent? Could the flow we experience be a byproduct of deeper, timeless structures? As we move into the next part, we will explore exactly that possibility, examining whether time is truly fundamental, or whether it arises from more basic processes that exist beyond our intuitive understanding of past, present, and future. At first glance, time feels unavoidable. Everything we experience appears to happen in time. Thoughts follow one another. Moments seem to arrive, linger briefly, and then disappear into memory. From this perspective, time feels more basic than space, more intimate than matter, more real than anything else we can point to. And yet, when physics digs deeper into the structure of reality, time begins to lose this privileged status. Some of the most advanced theories in modern physics suggest a possibility that feels almost heretical to intuition. Time may not be fundamental at all. It may emerge from something deeper, something that does not resemble time in any familiar sense. To understand why scientists even consider this idea, we must look at a growing tension within physics itself. General relativity describes space-time as a smooth, continuous fabric, one that bends and curves in response to mass and energy. Quantum mechanics, on the other hand, describes reality as discrete, probabilistic, and fundamentally non-continuous. Both theories work extraordinarily well in their own domains. Both have been tested with incredible precision, and yet they do not fit together. When physicists attempt to describe situations where both strong gravity and quantum effects are present, such as inside black holes or at the beginning of the universe, the equations break down. Time, in particular, becomes problematic. In quantum mechanics, time is treated as an external parameter, a background against which change occurs. It is not something that fluctuates or behaves quantum mechanically. It is assumed. In general relativity, time is part of the dynamic geometry of space-time, influenced by matter and energy. It is not fixed. It is shaped. These two views of time are incompatible at a deep level. To resolve this conflict, some approaches to quantum gravity suggest that time may not exist at the most fundamental level of reality. Instead, what we experience as time may emerge from relationships between more basic, timeless elements. In these theories, the universe at its deepest level is not evolving in time. It simply exists as a network of relations, configurations, or states. Change, duration, and sequence arise only when these states are compared in certain ways. One way to think about this is through analogy. Temperature feels fundamental. We experience it directly. Yet temperature does not exist at the level of individual particles. A single molecule has no temperature. Temperature emerges from the collective behavior of many particles moving together. In the same way, time may emerge from the collective behavior of more fundamental components of reality, becoming meaningful only at larger scales where structure, memory, and entropy exist.
In some theoretical frameworks, such as loop quantum gravity, the fundamental building blocks of the universe are not points in space-time, but discrete elements connected by relationships. There is no global clock ticking in the background. Instead, time arises when these elements interact, creating correlations that can be ordered and compared. In other approaches, such as the holographic principle, space-time itself may emerge from quantum information stored on lower dimensional boundaries. In these models, time is not a basic ingredient. It is a property of how information changes. Even more radically, some theories suggest that the universe as a whole may be described by a timeless equation, one that contains all possible configurations at once. From within such a universe, observers perceive time because their consciousness follows a particular path through these configurations, creating the experience of sequence. In this view, time is not something that flows, it is something that is experienced. The universe does not move from past to future. Observers move. This idea aligns strangely well with the block universe picture suggested by relativity, where past, present and future all coexist within space-time. What we call the present may simply be the point at which consciousness intersects the structure of reality. This does not make time unreal in any practical sense. Emergent phenomena are not illusions. Sound is emergent. Waves are emergent. Life itself is emergent. They are real, even if they are not fundamental. If time is emergent, it means that our experience of time is deeply tied to memory, entropy, and the organization of information. We experience a past because records exist. We experience a future because it is not yet recorded. The flow of time may arise from how information is stored and processed within physical systems. This also sheds light on why time has an arrow. If time emerges from entropy, then its direction is not imposed by the universe, but by the statistical structure of states. The arrow of time is not built into the foundations of reality. It appears when conditions allow entropy to increase. This means that time's flow, its direction, and its meaning may all depend on the state of the universe, not on timeless laws. At the deepest level, reality may be more like a static landscape than a flowing river. Change occurs not because time moves forward, but because different parts of the landscape are related in ways that allow observers to experience sequence. This challenges almost every intuitive assumption about existence. It suggests that the universe is not happening, it is, and within it, consciousness traces paths that feel like becoming. Whether time is truly emergent or fundamental remains an open question. There is no final answer yet, but what is clear is that time is far stranger than it appears, far less absolute and far more subtle than everyday experience suggests. The deeper physics goes, the more time dissolves into relationships, correlations, and structures that do not resemble a ticking clock. And as we move into the next major part, we will explore how this strange nature of time affects causality, determinism, and the limits of what can be known, revealing that space-time is not just the stage of reality, but one of its most profound mysteries. Time feels like the most dependable feature of reality because it accompanies every experience without ever asking permission. It appears steady, impartial, and universal, moving forward at the same pace for everyone, everywhere, forming the invisible backbone of cause and effect, memory and anticipation, life and decay. This feeling is so convincing that for thousands of years it went almost unquestioned. Yet this sense of a shared, universal flow of time is not something the universe provides. It is something the human mind constructs. When physics looks closely, time refuses to behave like a single river, carrying all of reality forward together. Instead, it fractures into countless local flows, each shaped by motion, gravity, and geometry, none of which can claim absolute authority. The idea of universal time came from everyday experience. At human speeds and in weak gravitational fields, clocks stay synchronized well enough that differences are negligible. The sun rises for everyone on Earth at roughly the same rate. A second feels like a second everywhere we go. But this apparent universality is an illusion produced by limited conditions. When those conditions change, time changes with them. Relativity reveals that time is inseparable from space, forming a four-dimensional structure called space-time, where time is not an independent backdrop, but one coordinate among others, woven directly into the geometry of reality. This alone is enough to undermine the idea of a universal flow. In space-time, different observers carve reality into moments in different ways. What one observer calls now is simply a slice through space-time that depends on their motion. Another observer, moving differently, slices the same structure at a different angle, producing a different set of events they consider simultaneous. There is no master slice, no cosmic present. Two events separated by distance may be simultaneous for one observer and not for another, and there is no experiment that can decide which perspective is correct, because the laws of physics treat all inertial observers equally. This destroys the idea that the universe shares a single moment of time. Instead, the universe consists of events related by geometry and causality, not by a universal clock. Time becomes local. Each observer carries their own clock, ticking according to the path they follow through space-time. This path, called a world line, determines how much time they experience between events. Two observers may begin together, separate, and reunite, having aged differently, not because time malfunctioned, but because time never flowed universally in the first place. This is not merely theoretical. Atomic clocks placed on airplanes, satellites, and mountaintops tick at different rates. Clocks in orbit run faster than clocks on Earth's surface. Clocks on fast-moving objects run slower than stationary ones. Time responds to conditions. It bends, it stretches, it slows. And none of this requires interpretation or philosophy. It is measured, predicted, and corrected for in real systems every day. Once we accept that time is local, another assumption quietly collapses. The idea that past, present, and future are absolute divisions built into reality. In relativity, these divisions depend on the observer. Events that lie in the future of one observer may lie in the past of another, provided those events cannot influence each other causally. Causality is preserved, but temporal ordering is flexible. This flexibility is not chaos, it is structure. The universe enforces a strict limit on influence through the speed of light. Events inside each other's light cones have a fixed causal order. Events outside do not. Time's order exists where influence exists. Everywhere else, the distinction between past and future becomes observer-dependent. This leads naturally to the idea often called the block universe, where space-time is treated as a complete four-dimensional structure containing all events, rather than a three-dimensional world evolving moment by moment. In this view, time does not flow. Instead, observers move through space-time, experiencing events in sequence along their world lines. The feeling of flow arises from consciousness, memory, and entropy, not from time itself doing anything. The universe is not becoming, it simply is. This does not mean the future is fixed in a naive sense, nor does it deny uncertainty or free choice. It means that physics does not require a global moving present to function. Change happens because different events are related differently, not because time advances like a ticker tape. This perspective feels deeply unsettling because it conflicts with direct experience. We remember the past, not the future. We feel time passing. But these experiences arise from physical processes inside the brain that themselves depend on entropy, memory formation, and irreversible change. They are real experiences, but they are not proof that time flows universally. They are proof that we are physical systems embedded in space-time, following particular paths through it. The lack of universal time also means there is no single age of the universe shared everywhere. The universe does not have one global clock marking its age in the same way everywhere. Different regions, influenced by different gravitational conditions, experience cosmic history at slightly different rates. The age we quote for the universe is a convenient measure tied to a particular class of observers moving with the cosmic expansion, not an absolute property of reality. Time, in other words, is contextual. It depends on where you are, how you move, what gravitational field you inhabit. Remove motion and gravity, and time loses structure. Remove structure, and time loses meaning. This reveals something profound. Time is not the container in which reality unfolds. It is one of the ways reality relates to itself. Understanding this does not make time disappear. It makes it more precise. Time becomes a measure of separation between events along paths in space-time, not a universal rhythm imposed on the cosmos. And once this is accepted, an even deeper question emerges, one that reshapes everything we think we know about existence. If time is not universal, if it depends on structure and conditions, could it be that time itself is not fundamental at all, but something that emerges only when the universe is organized in certain ways? That question leads directly into the next part, where the direction of time, its arrow, and its dependence on entropy begin to reveal just how fragile and conditional our experience of time really is. Even after accepting that time is not universal, that it flows differently depending on motion and gravity, there remains one aspect of time that feels stubbornly absolute and impossible to escape: its direction. No matter where we are or how fast we move, time seems to point one way. We remember the past, not the future. We grow older, not younger. Causes come before effects. This one-way character of time is so deeply embedded in experience that it feels more fundamental than space itself. Yet here lies one of the greatest surprises in physics. At the deepest level known to science, the fundamental laws of nature do not contain a preferred direction of time. The equations that govern particles, forces, and fields work almost perfectly the same whether time runs forward or backward. If you were to record the microscopic motion of atoms colliding, electrons interacting, or planets orbiting, and then play that recording in reverse, the equations would still be valid. Nothing in those laws tells the universe which way time is supposed to flow. So where does the arrow come from? Why does the universe clearly distinguish past from future, even though its deepest rules do not? The answer does not lie in time itself. It lies in entropy. Entropy is often described as disorder, but this is an oversimplification. More precisely, entropy measures how many microscopic arrangements correspond to a given macroscopic state. A highly ordered state can be realized in very few microscopic ways. A disordered state can be realized in enormously many ways. Nature does not prefer disorder in a moral sense, it simply follows probability. Systems evolve from unlikely states to likely ones. This statistical tendency is what creates the arrow of time. When entropy increases, time points forward. When entropy decreases, time would appear to run backward. The universe we inhabit began in an extraordinarily low entropy state. This is one of the most important facts in cosmology. The early universe was hot and dense, but remarkably smooth and uniform, an arrangement that was highly ordered given the amount of energy present. This low entropy beginning allowed entropy to increase as the universe expanded. Stars formed, galaxies clumped, structures emerged, heat flowed from hot regions to cold ones, entropy increased, and with it, time gained direction. Every irreversible process you have ever observed is a manifestation of this increase. A cup falls and shatters, but never reassembles itself. Smoke spreads through a room, but never gathers back into the flame. Ice melts, but never spontaneously reforms in a warm glass. These processes are not forbidden in reverse by the laws of physics. They are forbidden by probability. The reverse processes would require an astronomically precise coordination of microscopic motions, so unlikely that they effectively never occur. This statistical asymmetry gives time its arrow. Memory itself depends on entropy. To remember the past, the brain must form physical records, changing neural structures and consuming energy. This increases entropy. Remembering the future would require entropy to decrease, which does not happen. This is why memory only works in one direction. Causality, as we experience it, also depends on entropy. We interpret causes as preceding effects because the formation of effects involves irreversible processes that increase entropy. The arrow of causation follows the arrow of entropy. Even the sensation of time flowing arises from this same source. The brain is a physical system operating far from equilibrium, constantly dissipating energy. This dissipation gives rise to a sequence of internal states that feel like a moving present. Without entropy increase, consciousness as we know it could not exist. What makes this even more striking is that the arrow of time is not built into space-time itself. Relativity allows time to bend, slow, and fragment, but it does not dictate which direction time must point. The geometry of space-time is time-symmetric. The arrow is imposed by boundary conditions, not by laws. Specifically, it is imposed by the universe's initial state. If the universe had begun in a high entropy condition, time would not have had a clear direction at all. Processes would not unfold in a meaningful sequence. Complex structures would not form. The universe would be static in every sense that matters. The fact that time has a direction is therefore not inevitable. It is contingent. It depends on how the universe began. This realization has profound consequences. It means the arrow of time could, in principle, fade or even disappear. As the universe evolves toward higher and higher entropy, energy gradients diminish. stars burn out, matter spreads thin, differences flatten. In a far future universe near maximum entropy, there may be no meaningful arrow of time left. Events would still occur in a technical sense, but nothing would distinguish one moment from the next. No clocks would tick in a meaningful way. No processes would mark change. Time would still exist mathematically, but not experientially. The arrow would dissolve. This also means that the arrow of time is not universal across all possible universes. Different universes with different initial conditions could have different arrows, or none at all. Time's direction is not a law, it is a consequence. And this raises an even deeper question. If the arrow of time depends on entropy, and entropy depends on the universe's structure, then perhaps time itself is not fundamental. Perhaps time emerges only when conditions allow entropy to increase, memory to form, and processes to unfold irreversibly. This idea leads directly into the next part, where we confront one of the most radical possibilities in modern physics, that time, like temperature or pressure, may be an emergent phenomenon arising from deeper, timeless foundations of reality. Time feels so immediate, so unavoidable, that questioning its fundamental nature can feel almost meaningless, as if one were trying to doubt the existence of thought while thinking. Every experience seems to unfold in time. Every action appears to require it. Every memory depends on it. And yet, when physics pushes past intuition and into the deepest layers of reality, time begins to look less like a basic ingredient of the universe and more like a consequence of something deeper. This idea is not philosophical speculation. It arises from a serious and persistent problem at the heart of modern physics. Our two most successful theories describe reality in radically different ways. General relativity tells us that space and time form a smooth, continuous fabric that bends and curves in response to mass and energy. Time, in this picture, is dynamic. It stretches, slows, and responds to gravity. Quantum mechanics, on the other hand, describes the universe in terms of discrete states, probabilities, and interactions between fields and particles. In this framework, time is not dynamic at all. It is assumed to exist in the background, fixed and external, like a silent referee watching the game. These two pictures cannot both be fundamental. When physicists try to merge them into a single theory of quantum gravity, time becomes the central problem. In many attempts to quantize gravity, time simply disappears from the equations. This is not because physicists removed it by choice. It is because the equations work without it. In some formulations, the most fundamental description of the universe is timeless. There is no variable corresponding to time at all. This leads to a deeply unsettling possibility. Time, as we experience it, may not exist at the most basic level of reality. Instead, it may emerge. To understand what this means, consider how other familiar concepts behave. Temperature feels fundamental. You feel it directly. Hot and cold seem basic. Yet temperature does not exist at the level of individual particles. A single atom has no temperature. Temperature emerges only when many particles interact, producing collective behavior that can be summarized by a single number. Pressure works the same way. So does sound. So does fluid flow. None of these are illusions. They are real, measurable, and powerful, but they are not fundamental. Time may be similar. At the deepest level, the universe may consist of relationships between states, configurations, or bits of information with no built-in notion of before and after. Sequence arises only when certain conditions are met. In this view, time is not something that flows. It is something that is inferred. Some theories suggest that time emerges from change. If nothing changes, time has no meaning. Imagine a universe frozen in a single configuration, with no variation, no interaction, no difference between states. In such a universe, asking how much time has passed would be meaningless. Time requires comparison. It requires at least two distinct states and a rule for ordering them. In a timeless fundamental theory, reality may be described as a vast collection of possible states, all existing at once without sequence. What we experience as time is the process of moving through a subset of these states in an ordered way. But what determines that order? One answer comes from entropy. As we explored earlier, entropy provides a direction, an arrow. If the fundamental state of the universe allows entropy to increase, then sequences of states naturally form, ordered by increasing entropy. Time emerges as a way of labeling that order. In this picture, time is not primary. Entropy is. Time is a bookkeeping tool for tracking change in entropy. This idea fits remarkably well with the arrow of time. We experience time flowing forward because entropy increases forward. If entropy were constant, time would lose direction. If entropy decreased, time would appear to run backward. Another approach suggests that time emerges from quantum entanglement. In some models, the correlations between quantum systems give rise to an effective notion of time. Systems that are strongly entangled evolve in ways that can be ordered relative to one another, creating an internal clock. Time becomes a measure of correlation change, not a fundamental parameter. From this perspective, time is not universal. Different subsystems may experience different effective times, depending on how they are entangled with the rest of the universe. This aligns eerily well with relativity's conclusion that time is local. Some approaches go even further. They suggest that the universe as a whole may be described by a single, timeless equation that contains all possible configurations of reality. Nothing evolves, nothing happens, everything simply is. Within this static structure, observers exist as patterns, and their consciousness traces paths through the structure that feel like motion, flow, and becoming. Time, in this view, is not a feature of the universe, it is a feature of experience. The universe does not move from past to future. Observers do. This does not mean the future is fixed in a simplistic sense. Quantum uncertainty still exists. Choices still matter within paths, but the overall structure does not require a moving present. This idea is deeply uncomfortable because it contradicts how we live. We plan, we wait, we remember. Yet physics is not required to align with intuition. Reality has already taught us that Earth is not central, that space is curved, and that time slows near gravity. The idea that time itself might not be fundamental is simply the next step in that pattern. If time is emergent, then questions like, what happened before the Big Bang, may be ill-posed. Before requires time. If time itself emerged at the Big Bang, then there is no before in the usual sense. The Big Bang may not be a beginning in time, but the beginning of time. Or more subtly, it may be a transition between timeless and time-like regimes. This also changes how we think about endings. If time is emergent, it may not truly end, it may dissolve. As entropy reaches a maximum, as change fades, as gradients disappear, time may lose meaning, not because something dramatic happens, but because nothing happens anymore. Time would not stop. It would become irrelevant. This perspective also reframes the human experience. Our sense of time flowing may arise from how our brains process information, store memories, and operate far from equilibrium. Consciousness itself may be a time-generating process. If so, then time is not something we're inside. It is something we are constantly creating through interaction with the universe. This does not make time unreal. Emergent phenomena are real. Waves are real. Life is real. Meaning is real. They are not fundamental, but they matter. If time is emergent, it is no less important for that fact. It simply means that time is not the deepest layer of reality. Beneath it lies something quieter, stranger, and more abstract. A structure that does not flow, does not age, and does not become, but from which all becoming arises, and this realization may be the most mind-blowing fact of all. Not that time bends, not that time slows, not even that time began, but that time itself may be a surface phenomenon, a shadow cast by deeper laws that do not experience past, present, or future at all. At the deepest level, space-time is not just a stage on which events occur, nor merely a fabric that bends and stretches. It is also a system of rules that determines what can influence what can be known, and what must forever remain unreachable. These rules are not philosophical preferences. They are hard limits built into the structure of reality itself. This is where causality enters. Causality is the principle that causes precede effects, that information flows in an ordered way, and that events are connected through influence rather than coincidence. Without causality, the universe would not merely be strange, it would be incoherent, and causality is enforced not by time alone, but by space-time geometry. In space-time, every event is surrounded by a structure known as a light cone. This cone defines all possible directions in which influence can travel. Events inside the future light cone can be affected. Events inside the past light cone could have caused it. Events outside both are fundamentally disconnected. No signal, no force, no information can cross these boundaries. This is not a limitation of technology. It is a limitation of reality. The speed of light is not just the speed at which light travels. It is the speed at which causation itself propagates. Anything faster would allow effects to appear before causes, collapsing the logical structure of the universe. This means that space-time does not merely allow events, it filters them. It decides which connections are possible and which are forbidden. Even though time is relative and local, causality is absolute. Observers may disagree about simultaneity, about duration, about order of distant events, but they will always agree on causal structure. No observer will ever see an effect occur before its cause within their own light cone. This is how the universe preserves coherence even while time bends and fragments. Causality survives flexibility. Yet causality also imposes limits on knowledge. There are regions of the universe that can never influence us, no matter how long we wait or how advanced our technology becomes. These regions lie beyond our cosmic event horizon. Their light will never reach us. Their history will never be observed. Their existence can be inferred mathematically, but never confirmed directly. This is not because the universe is hiding information. It is because space-time itself prevents interaction. In this sense, ignorance is built into reality. There are facts that exist but are not knowable in principle. This challenges a deep assumption of science, that with enough time and technology, everything can be known. Space-time disagrees. It allows prediction only within causal boundaries. Beyond those boundaries, even perfect theories remain silent. Causality also explains why time travel into the past is so problematic. If effects could influence their own causes, paradoxes would arise, not as storytelling devices, but as breakdowns of logical consistency. Space-time geometry strongly resists this. While some solutions of Einstein's equations mathematically allow closed time-like curves, every known realistic mechanism that would create them also destroys the conditions needed to maintain causality. The universe appears to protect its own consistency. This protection is sometimes called chronology protection. Time may bend, time may slow, but time does not fold freely. Causality acts like a guardrail, preventing the most destructive possibilities. This does not mean the universe is simple or safe. It means it is structured. Causality also governs uncertainty. Even in quantum mechanics, where outcomes are probabilistic, causality still limits what correlations can exist. Quantum entanglement allows strange, non-local correlations, but it does not allow faster-than-light communication. Information remains bound by space-time. The universe permits mystery. It does not permit contradiction. This interplay between flexibility and constraint is one of the most remarkable features of space-time. Time is relative. Space is dynamic. Yet, causality remains firm. This balance allows complexity without chaos. Without it, stars could not form reliably. Life could not persist. Memory could not exist. Causality gives the universe its narrative structure, even if that narrative has no universal timeline. As we move deeper into this part, we will see that causality not only limits influence, but also defines the ultimate boundaries of prediction, computation, and knowledge itself. Some questions are not unanswered because we lack intelligence. They are unanswered because space-time forbids the answers, and understanding that distinction changes how we think about reality, science, and our place within the universe. If causality defines what can influence what, then event horizons define where influence ends altogether, marking absolute boundaries beyond which information cannot return. Not because it is hidden or destroyed, but because space-time itself prevents the connection. An event horizon is not a physical surface. It has no texture, no thickness, no material substance, and yet it is one of the most powerful structures in the universe. It is a boundary in space-time. Once crossed, return becomes impossible. The most familiar example is the event horizon of a black hole, a region where gravity has curved space-time so intensely that all possible paths forward lead deeper inward and no path leads back out. At the event horizon, escape velocity equals the speed of light. Beyond it, even light cannot return. But this does not mean information is destroyed at the horizon. From the perspective of an object falling in, nothing special happens at the moment of crossing. Space-time remains smooth. Local physics behaves normally. The laws of nature do not suddenly change. It is only from the perspective of a distant observer that the horizon becomes meaningful. To that observer, signals from the falling object slow, redshift and fade, never quite disappearing, but never delivering confirmation of what happens next. This creates a profound asymmetry in knowledge. Two observers can disagree forever about what happens beyond the horizon, and neither can prove the other wrong. Reality itself allows multiple, incompatible descriptions to coexist, each valid within its own causal frame. This is not a failure of physics. It is a feature of space-time. Event horizons do not merely limit travel, they limit knowledge. They divide the universe into regions that can be observed and regions that can only be inferred. This idea extends far beyond black holes. The expanding universe itself has an event horizon. Because space expands and that expansion accelerates, there are distant regions of the cosmos whose light will never reach us, even given infinite time. Those regions are not outside the universe. They are inside space-time, but causally disconnected. Their galaxies may exist forever without ever interacting with ours. Their histories may unfold without ever being known. This means the observable universe is not the universe. It is a causally connected patch within a much larger, possibly infinite whole. Everything we have ever seen, measured or inferred directly lies within this patch. Beyond it lies a realm that is real, but permanently inaccessible. This changes the meaning of scientific completeness. Even a perfect theory of physics cannot predict the detailed state of regions beyond our horizon, because no information from those regions can reach us. At best, we can make statistical statements based on symmetry and theory. This introduces a new kind of uncertainty, not due to randomness or ignorance, but due to causal separation. There are facts that exist but cannot, even in principle, be known. Event horizons also challenge the idea that the universe is fully deterministic in an observable sense. Even if the laws of physics are deterministic at a fundamental level, horizons prevent complete information from being available to any single observer. No observer can access the entire state of the universe. This has deep implications for predictability. A system may evolve according to precise laws, but if part of its state lies beyond a horizon, its future behavior may be fundamentally unpredictable from within. This is not because the future is random, but because information is missing and cannot be recovered. Black holes push this issue to an extreme. When matter falls into a black hole, information about its detailed state appears to be lost behind the horizon. For decades, physicists debated whether this information is destroyed or preserved in some subtle way. This debate, known as the black hole information paradox, revealed something astonishing. The limits of observation imposed by horizons are so severe that they challenge our deepest assumptions about reality itself. Modern research suggests that information is not destroyed, but encoded in ways that are inaccessible to ordinary observation, possibly stored on the horizon itself in a highly scrambled form. This idea led to the holographic principle, which proposes that all the information contained within a region of space may be encoded on its boundary. If true, this means that the universe stores information in ways radically different from everyday intuition. Volume becomes secondary, surface becomes fundamental. Space-time itself may be an emergent description of deeper informational relationships. Event horizons thus act as gateways to the deepest layers of physics. They reveal that space-time is not just geometry and motion, but also a system for managing information. What can be known? What can be shared? What must remain hidden? This reframes the idea of mystery. Some mysteries exist not because we lack intelligence, but because reality itself forbids resolution. No experiment can reach beyond an event horizon. No signal can cross it. This is not a technological problem, it is a structural one. Yet within these limits, the universe remains astonishingly rich. Event horizons do not eliminate meaning or discovery. They define the arena in which discovery is possible. They remind us that knowledge has boundaries, and that those boundaries are not arbitrary. They are written into the fabric of space-time. At first glance, the universe appears to be governed by rules that are precise, mathematical, and unbreakable. Equations describe how particles move, how fields interact, how space-time bends, and how energy flows. This precision tempts us toward a powerful idea that if we knew all the laws and all the initial conditions, the future would be completely predictable. This idea is called determinism. For a long time it seemed unavoidable. If the universe is a machine, then knowing its state at one moment should allow us to calculate its state at any other moment. But space-time does not allow such a simple picture. The deeper physics goes, the more it becomes clear that perfect prediction is impossible, not because the universe lacks rules, but because space-time itself blocks access to the information those rules would require. Determinism breaks not at the level of laws, but at the level of access. Causality, as we explored, limits what can influence what. Event horizons place absolute boundaries on observation. Information can exist without ever being available. This alone is enough to undermine full predictability. Even in a universe governed by deterministic equations, no observer can ever know the complete state of the universe, because parts of that state lie beyond causal reach. Prediction requires information. Space-time withholds it. This means uncertainty is not always about randomness. It is often about separation. A future event may be fully determined by past events that lie outside an observer's light cone. From the observer's perspective, the future is unknowable, even though it is not undetermined. This creates a subtle but profound distinction between ontological determinism and epistemic unpredictability. The universe may evolve according to strict rules, yet no observer within it can ever fully predict that evolution. Knowledge is local, reality is global. Space-time enforces this gap. Quantum mechanics deepens the issue. At the quantum level, uncertainty is not merely about ignorance. It is built into the structure of reality. The Heisenberg uncertainty principle does not say that we fail to measure precisely. It says that certain pairs of properties cannot both be precisely defined at the same time. This is not a technological limitation. It is a structural one. Yet even here, causality remains intact. Quantum uncertainty does not allow effects to occur without causes. It limits what can be known simultaneously. Randomness enters not as chaos but as constraint. When quantum uncertainty combines with space-time horizons, predictability erodes even further. Information can be lost behind horizons. Measurements are limited by uncertainty. Initial conditions are incomplete. Together, these features ensure that no observer can ever become a perfect predictor, no matter how advanced. This has implications that reach beyond physics. It reshapes how we think about free will. If the future is not fully predictable from within the universe, then the question of freedom becomes more subtle. Freedom does not require the universe to lack laws. It requires that outcomes are not fully constrained by information available to the agent. Space-time provides exactly that condition. choices propagate forward causally. They are not overwritten by future states. They are not perfectly predictable by any external observer. This does not prove free will in a philosophical sense, but it shows that physics does not eliminate it. Determinism does not imply control. Another implication concerns computation. There are limits to what can be computed, not just because of finite resources, but because information required for computation may lie beyond causal horizons. Some problems are not hard because they are complex. They are hard because the universe withholds the data. This creates a fundamental ceiling on prediction. No supercomputer can calculate what it cannot know. No equation can solve what space-time hides. Even chaos theory reinforces this lesson. In chaotic systems, tiny differences in initial conditions lead to wildly different outcomes. If initial conditions cannot be measured perfectly, prediction collapses rapidly. Space-time ensures that such perfect measurement is impossible, not because instruments are weak, but because information is incomplete and irretrievable. The universe does not permit omniscience from within. This is not a flaw, it is a feature. A universe that allowed total prediction from any point would be static in a deep sense. Everything would already be known. Uncertainty, surprise, and novelty would vanish. Space-time preserves openness. It allows laws without locking outcomes into complete transparency. This balance between order and unpredictability is what allows complexity to flourish. Stars form without being perfectly predictable. Life evolves without being pre-written. Consciousness arises without being reducible to foresight. The universe is lawful, but not legible in full. Causality defines what can happen. Horizons define what can be known. Uncertainty defines what must remain open. Together they ensure that the universe is not a closed book, but an unfolding structure that can never be fully read from any single page. This realization is not discouraging. It is liberating. It means that mystery is not a temporary condition waiting to be eliminated. It is woven into the architecture of space-time itself. There will always be questions that cannot be answered, not because we failed, but because the universe does not allow the answers to be reached. And yet, within these limits, meaning persists. We observe, we predict locally, we choose, we explore. Not in spite of uncertainty, but because of it. Space and time feel familiar because we live inside them, yet the deeper we look, the more they dissolve into something stranger and more fragile than intuition suggests. What seems solid bends. What seems absolute depends on perspective, and what feels knowable reveals limits written into reality itself. Perhaps the universe is not meant to be fully understood from within, but slowly approached, layer by layer, question by question. And maybe that quiet mystery is not a flaw of existence, but its final design.